Good morning, student. How are you? I hope you are all fine. Our topic today is equilibrium of bodies in liquid. So let us proceed. It is our common experience that object appears to become lighter when partly or completely immersed in a liquid, such as water. For example, if one draws a bucket full of water out from a stream, the bucket appears lighter when inside the stream and then appears heavier and heavier as it leaves the stream. It appears heaviest when completely out of the stream. This simply means that when you drop a bucket of water, a paid bucket of water, a pail bucket that does not contain any water, you drop it inside stream to fetch water out of the stream or a well. Once the bucket fetch water, the bucket will sink down to the bottom of the water, right? I believe you understand that if you actually have done that before. Then to draw the bucket out from the water, you can use one of your hand to draw the bucket out. The bucket will be coming out lightly without applying much effort. By the time the bucket gets to the surface of the water, the bucket appears to be more heavier than it was in the water. The reason is this: when the bucket was under the water, there is an upward force exerted by the water on the object, which is helping you to push the bucket out. Now when the bucket is totally outside the water, you experience or you feel the total weight of the object. At this point, you need to apply your two hands to draw the bucket from the water. So let's proceed. This experience suggests that there is upward force exerted by the liquid on anything immersed partly or completely in it. There is thus an apparent weight of such objects due to this upward force. This upward force is called the upthrust. If the true weight of an object in air is W1 and the apparent weight in a liquid is W2, when you weigh the object in air, you call that W1. When the object is immersed in a liquid, weigh it with spring balance, you are going to have W2, which is apparent weight. The upthrust is denoted by U. Then U is given by U is equal to W1 minus W2. W1 is weight in air, while W2 is apparent weight of the object when immersed in the liquid. Hence, W2, the apparent weight when immersed in the water, is given by W2 is equal to W1 minus U, where U is the upthrust and W1 is weight in air. Hence, W2 is less than W1. The apparent weight is always less than the real weight of the object. The value of the upthrust is depend on the volume of the solid immersed. The volume of the solid immersed and the density of the object. Let me repeat that. The value of the upthrust or the magnitude of the upthrust exerted by the water, by the liquid, depends on two factors. Number one factor is the volume of the solid immersed. The volume of the solid immersed in the liquid. And number two is the density of the liquid immersed into which the solid immersed in. Again, two factors in which the upthrust depends on. Number one, the volume of the object immersed in the liquid, and number two, the density of the liquid into which the object immersed. If you look at the diagram below, you see what I mean. The object sinking down the surface, sinking down below water, has its weight acting downward W, and the upthrust acting upward, which is U. Let's proceed. The magnitude of the upthrust is given by the Archimedes principle. Let us state that Archimedes principle states that when a body is totally or partly immersed in a fluid, liquid or gas, it experiences an upthrust which is equal to the weight of the liquid displaced. Let me come again. Archimedes principle states that when a body is totally or partly immersed in a fluid, it experiences an upthrust which is equal to the weight of the liquid displaced. Let me quickly cite an example on that. Let's say you have a bucket, or you have a bucket in front of you, and this bucket, you fill up the bucket with a little water, then you mark the level at which the water is. Immediately you drop an object inside the bucket of water, then the level of the water will rise to a new length. So that new length, you call it L2. So subtract the original level of water, which is L1, from the new level of water L2 when you drop an object in it. Now the quantity of volume of liquid between these, when you subtract L1 from L2, the volume you have here, the volume you have is the volume of the object immersed in the liquid. So the quantity of the water displaced, the quantity of the water displaced or the weight of the water displaced represent the weight of the object immersed in it. Any object completely immersed in a liquid displaces a volume of liquid equal to the volume of the object. That is what I've just explained. The upthrust is the weight of this volume. The upthrust is the weight of this volume of the liquid and is given by. So when the volume of object is displaced, convert this volume to force or convert this volume to weight multiplied by density, gravity gives you the upthrust. So the volume displaced now, how do we turn into force? Simple. What you do that, then the volume of the object displaced. I told you density, upthrust depends on two factors: volume of the object immersed in water and the density of the liquid in which the object immersed on. And the volume of object immersed is also equal to the volume of the water displaced when totally immersed. Volume of the object, if you cannot find the volume of the object, just drop the object in the liquid, then the rise in volume of the liquid become the volume of the object. Do you understand now? So the volume of the water displaced or the volume of the object times the density of the liquid times the gravity, acceleration due to gravity, will be given as volume of the water displaced or volume of the object is m cube times density is mass over volume, which is kilogram over meter cube, times acceleration due to gravity, which is meter per second square. So when you multiply this together, the final answer is Newton, which means the upthrust force is now the answer in Newton. So let's proceed. If the object is only partly submerged in water, e.g. 1/3 of the volume of the object in water, then the upthrust is given by, the upthrust is equal to, since we know that 1/3 of the object is what is immersed in water, that means the volume of the water displaced or the volume of the liquid displaced will also be 1/3 of the volume displaced. So if the object is 1/3, if 1/3 of the object is immersed, therefore the volume in water displaced by the object in water is volume of the water divided volume displayed divided by 3. So volume of the object divided by 3 will give you the volume, since the object is partly immersed, times the density of the liquid times the gravity. So that is the way we'll treat it when the object is partly immersed in the liquid. Now we'll move on to flotation. Flotation, when objects float in water. So this has a principle, flotation. So when a piece of cork is pushed into water, the cork is seen to bob up when released due to the upthrust of the water on the cork. Because of the upthrust, a swimmer floats in water, a balloon floats in air, and ice cubes float in water. So principle of flotation state that an object will float in a fluid. Principle of flotation state that an object will float in a fluid when the upthrust exerted upon it by the fluid in which it floats equals the weight of the object. That is equilibrium of the object. Which this simply means that, again, principle of flotation states that an object will float in a fluid when the upthrust exerted upon it by the fluid in which it floats equals the weight of the object. So if the upthrust exerted by the object actually equals to its own weight, the object will do what? The object will float, because the object has attained equilibrium position. The weight of the object acting downward and the upthrust exerted on it acting upward. When the two of them equal one another, they cancel one another off, then the object is in equilibrium position. Therefore, the object will surely float. So that is the principle of flotation. So any object float is in equilibrium. Any object floating is in equilibrium under two forces. Number one force, its weight acting downward. Number two, the upthrust of the liquid on the object acting upward. So look at the diagram on the screen. You will see that the object there is floating in water, and the weight of the object is downward while the upthrust is upward. So therefore, for this object to float, the weight must be equal to the upthrust. Let's proceed. So factors affecting flotation now. Factors affecting flotation. For any object to float in fluid, its density must be less than that of the fluid. Can you hear that? That is one major factor that affects flotation. One major factor that affects flotation For any object to float in fluid, its density must be less than that of the fluid. The fluid density must be higher than the density of the object that is floating. If it is shaped in way that its volume can displace its own weight of the fluid. Thus, for a body to float, its density and shape are important factors to consider. So for an object to float, its density and the shape are what important factor to consider. We have all seen canoe before, or a boat. You can see the way it's shaped like a V, like a fulcrum. The essence of that is for the object, the boat or the canoe, to displace larger percentage of water under it in order for the object to support it. So the shape of the object and the density of object is very important when it comes to flotation, or for object to attain equilibrium position in fluid. A ship floats in water because it displaces a larger volume of water, which is equal to its own weight. A balloon filled with gas lighter than air. The gas in the balloon is always lighter than air because it is what? A hot what? Air. So the air in the balloon is always lighter than the environmental air. So a balloon filled with gas lighter than air will float if the weight of the balloon and the air in it, which is its content, equals the upthrust of the air on the balloon. The vertical position of a submarine can be controlled by flooding or emptying its buoyancy tank. The vertical position of a submarine can be controlled by floating or emptying the buoyancy tank. When it is floating, the buoyancy tanks are empty. Water is pumped only into the buoyancy tank to submerge the submarine. Let's proceed. Now, density and relative density. Density is defined as the mass per unit volume of a material. Density is denoted by a symbol you see on the screen. The symbol is called rho, R-H-O, rho. Density is defined as the mass per unit volume of a material, that is, mass over volume. So the SI unit of density is kilogram per meter cube, but in laboratory work, the smaller unit of gram per cm cube may be found necessary. Conversion of centigram per second to SI units. For example, density of water at 4 degrees Celsius is approximately to 1 gram per cm cube of water. How do you convert that? 1 gram per cm cube, the same thing as 1 gram all over cm cube, which is equal to 1 times 10 to 1 gram is to kilogram is divided by 1000. That is 1 times 10 to the power of minus 3 kilogram. All over centimeter to meter is 100, is divided by 100. So that means 1 times 10 to the power of minus 2 times everything in bracket to the power of 3. So that will give us 10 to the power of 3 kilogram per meter cube. So relative density is defined as follows. Rg, which represents relative density, is mass of a substance all over mass of equal volume of water, or weight of a substance all over weight of equal volume of water. So mass of a volume of water is chosen in this definition because water is most common liquid. So relative density is also defined by Rd is equal to density of substance all over density of water. So relative density has no unit. Relative density does not have units. Measurement of relative density of solid in form of particles or powder, e.g. sand. The relative density bottle is filled with clean and dried and weighed empty. Cleaned and dried and weighed empty. It is then reweighed when about 1/3 full of the sand The relative density bottle containing the sand is now filled up with water and reweighed. Finally, the bottle is emptied, cleaned of any sand particles and filled with water alone. The weight of the bottle and water is obtained. Relative density of sand is calculated as follows. Mass of the empty bottle. The density bottle you weighed initially without pouring anything in it. Let its mass be equal to M1. The mass of the bottle plus sand. When you weigh the bottle with sand in it, that is mass of bottle plus sand is equal to M2. So when you pour water, that will be mass of the bottle plus mass plus the sand plus water you pour in the bottle from the above explanation. Name that M3. So mass of the bottle plus water only. When you pour all the sand and water away, then pour water only into the bottle. So mass of the bottle and water only is M4. So mass of water filled with the bottle will be M4 minus M1, which is mass of the bottle plus water minus mass of the bottle only. So mass of water having the same volume of the sand is equal to M4 minus M1 in bracket, close the bracket, minus open another bracket M3 minus M2. So mass of the sand M2 minus M1. So relative density will be mass of sand all over mass of equal volume of water. So mass of sand is M2 minus M1. Then mass of equal volume of water is open bracket M4 minus M1, close the bracket, then minus open another bracket M3 minus M2. Then we'll go into practical hydrometer. The hydrometer. Hydrometer is an instrument used to measure the relative density of liquid. Hydrometer is an instrument used to measure the relative density of liquid. I think we'll stop our class here for today. So from tomorrow we'll continue.